All right, so today we're gonna review what we did a little bit in steering, and then we're gonna get into powertrain, so a little bit of engine and a little bit of drivetrain. So last time in steering, kind of the basics were, we looked at the car from the top. Well, this is a steering review. If these two tires are turning about this, this is the center of the turn. So this is what we're turning about. And if the center of the front right tire is here and the front left tire is here, these tires need to also be perpendicular to this point, right? And so same here. So all four tires will be perpendicular. To this point here. And this tire, we'll call this one right here theta left. And this angle, kind of how much this tire turned, is theta right. So we know for like a right-hand turn last time, right, that theta right must be greater than theta left. So your right tire turns in more, right? And the radius over here on the right compared to the radius over here on the left, that of course here you can kind of see the radius on the left is greater than the radius on the right, which was one reason if these wheels are driven to have a diff, right? Right, because they're gonna have to spin at different rates when they're going around that circle. But so to set up our car so that we get this to happen, basically, we set it up in what's called Ackermann geometry. So Ackermann geometry. Oh, before I get into Ackermann geometry, we had to talk a little bit about just some other angles on the tire, right? So if we had our tire, so maybe this was the inside and this was the outside of the car, and our upper ball joint connected here, upper ball joint, and our lower ball joint connected here. I'm gonna unmagnify that a little bit. Maybe that was look a little bit too much. It's still a lot. I can't draw a tire with just a little bit of camber. There you go. There's just a little bit of camber. So here's your upper ball joint, here's your lower ball joint. And right here, right, this was our steering axis. Steering axis. So this is what the tire rotated about, right? And so if we drew a vertical line right here, right, kind of the center of the tire on the ground vertically up, and we said this angle right here. So this was our kingpin inclination. So we call that like our KPI, right? And so we said our KPI was around usually kind of 5 degrees pointed towards our car to help with stability. And then we had this distance down here. So where this hits the ground, so we have this ground here. And so where this hits the ground versus here, we call that the scrub radius, right? And this scrub radius was usually larger than 0 and somewhere to like 2 inches. And like FSAE was probably in this range, and Baja was a little bit more over here. So formula is a little closer to 0, ease of steering basically. Baja we go a little closer to 2 to help with the weight shift and the stability of going over the big rocks, kind of straight line. Help us kind of keep the car driving straight. So, and then we also should keep in mind,
I heard max for us could be like 2 inches. That's like max.
Yeah, I think that would be like the max you would think about going. But I think it's going to make your tire harder to turn, and I don't know how much you need the stability. So I would think you would probably go, 0 to 1, somewhere between 0 and 1. I don't think you'd push out to 2.
Oh, okay. But I wonder, like, at least for Baja, like, if our max is 2 and you're at 2, what if you did like 4? What that would do? But then I think your tires are skinnier, right?
Yeah, they're, I think, a little bit skinnier. They're 7 inches wide, roughly. Our formula tires are 8 inches.
Oh, okay.
So
Then
not
that's
that
probably,
different, but
yeah.
a little. Yeah, I mean, it just would get really hard to turn, right? Because as that gets angled, as this gets angled in, you imagine as the tire like turns back, it like rotates in and down basically into the ground.
Uh-huh.
Right. So it's like it gets really hard to turn your wheels essentially. So it's, yeah, you probably don't want too much.
And then it's also feel, right? I think it's like feel, and then you could also heat up your tires that way.
Yeah, I'd probably heat up my tires a different way. I'd hate my tires up with cornering. I wouldn't like artificially heat my tire, like get my tires hot by having bad suspension geometry.
Chris, you want the kingpin in alignment with the center line of the wheel?
So in this one, probably do. So here, this is a side view with this is the front and the right. So you're talking about in this angle here, Bill?
Yeah.
So you definitely want, so this is your caster angle, right? So
Yeah.
this is your caster. And this is also, on the order of 5 degrees to help you with stability, kind of angled towards the rear of the car. I think what's most important is to get this distance here greater than 0. So this is your trail, and this better be greater than 0. So I think that provides more stability because your tire turns about this axis here, right? And so if for some reason you're turning about like an axis down here, that means if you had some forces like in and out of the page on your tire, it would like turn your wheel a lot. So it'd be really unstable. So you kind of want to so I think, you could shift this forward and back. I wouldn't see shifting it forward and back unless you had to. I'd probably center it about the tire, give yourself a little bit of caster, but make sure that your steering axis in the side view comes in front to give you what's a little bit of trail. And that's kind of the shopping cart analogy. It's kind of like the shopping cart's got a good 2-3 inches of trail behind that wheel. So it makes it stable basically. So we can step into a little bit of Ackerman geometry. A little bit of Ackerman geometry. So if we have this, scroll down. So if we have these 4 wheels, so again, we're looking at a top view. This is the front of the car. Here's the rear of the car. Remember your first steering setup one? I still remember those days.
My first setup?
Yeah, remember we messed up what Ackerman was in the first year, and so we had to like flip everything around like last minute, and we had no scrub radius.
Oh yeah.
Oh yeah.
Wait. Oh, that was when Luis was still doing front, right?
Yeah, I think Luis was doing front. You're right. That wasn't you.
No, I was doing the steering though.
Okay. Okay. So here's the steering axis in the top view, and so usually you draw a center line between your tires, and you put a point in the center. So this point's meant to be in the center, and then you draw a line from your steering axis, right? From your steering axis back down here, right? So these are your 2 steering axes. And to get it to do this Ackerman geometry, you want your connection to your rack. So let's put a rack here. So here's our rack. And at the end of the rack connects 2 tie rods. So I'll make my tie rods these colors. So for example, you have 2 tie rods. And at the end of the tie rods, let's say if you have good Ackerman geometry, you lie on this line. So this is Ackerman geometry right here. And remember that this was, oh, come on, sync. There you go. Remember that this was not completely accurate because your rack isn't necessarily right here in a straight line, and it's not a solid bar. So like Ackerman did this for like kind of a horse-drawn carriage. So like it had a single bar that went across. So now that you have your rack, this is kind of like an initial setup, and then you want to test it with that model that we used. But so this will give you Ackerman, which will set up that so your right tire turns a little more than your left tire on a right-hand turn and gets it upright. So so like deficient Ackerman. So if you set up like in this area, so let's say you have your tie rod, for example, connect here. So this would be like, you know, maybe you have, so these are your tie rods, right? So let's say you maybe come back here, something like this. And here's your rack again. And you draw these lines, they're going to come back and they're going to meet behind the rear of your car, basically. And what that means is your turning center is going to be in this range. It's going to be behind your wheels. So this is what we would call deficient Ackerman. So this is deficient. You don't have quite enough Ackerman, right? And that means your turn center is in here. Okay, so here you go, it's in here. Here's your turning center. Perfect Ackerman, your turning center is like right here. And then if you kind of go excess Ackerman, so let's say you kind of go, you connect your steering arm somewhere in here, basically. Then your turning center is going to come up in front. So here's where your turn center is. Right, and that would be the case where you make a connection here, or like a connection here to the end of your tie rod, which basically means your steering arm would look like this, right? So you'd have usually some steering arm coming off your upright. And so this line would look something like this. We'll just kind of pretend it's, and they would meet somewhere here, basically, right? So if you do this line from your steering axis through your mounting point to your tie rod, so we can kind of do a little rack. Here's like your little rack, you know. So if you have this mounting point and you draw a straight line and it goes to the front of the rear axis, then your turn center is gonna be in front, and that's because, so this point right here, right? So this was deficient Ackerman or excess Ackerman. Right, versus vice versa. If you have this connecting point go outside, then you draw this straight line, it's going to come behind, and then your turn center is going to come out in the back, right? So but make sure, right, this is just to get you in the, this analysis is just to get you in the ballpark, right? So you should really simulate what we did last time and see where the turn centers actually are with an actual rack and pinion system. Then we talked a little bit about bump steer, right? So we talked a little bit kind of about bump steer, which involves setting up your tie rod the right way. So for example, if we have, so in this case, this is maybe the outside of the tire. This is on the inside of the tire. So this is like a left, looking from the back, this would be a left-hand tire, or a left tire on the left-hand side. These are your upper arms, right? So we extend those out. And this point was our instant center, right? So that's what we kind of say our tire kind of moves around. So if we want to get, if we want to get it so that our tire doesn't toe in or out as it goes up and down, keeps the tire straight, then we want our tie rod to also point, so this is our tie rod, to also point to the instant center, and it should have this length. But the thing you can do is you can move it inboard and outboard. So that, because you imagine moving your tie rod inboard and outboard up here, right? You're gonna need to do that so you can get the right connecting point, right? So you can't, it's kind of an over-constrained problem. So in terms of this, we say that the tie rod must point at instant center, right? must be length. Must be length as shown above, right? But you can move it inboard or outboard. With a smaller penalty. I'm about to just switch off if these things are really going to be this slow. Okay.
You said with a small penalty? What do you mean?
Well, by penalty, I mean it's not going to be perfect, right? So I mean, so if you move it inboard and outboard, it's not the fact that you're not necessarily. Come on.
Like your length should change technically, or?
Yeah, I mean, so the thing of this is this is like, I mean, right, we're taking a static picture of something that's very dynamic, right? So as the tire moves up and down, your instant center moves around, right? And so like this, setting it up like this in a static condition does not mean you're never going to have any bump steer, basically, right? So you really have to actually make this kinematic model and move it around and see what the toe is like. And it's a 3D thing too, right? It's not a 2D thing also. So this is like get you really close to the ballpark, and then you kind of do a little bit of an actual CAD model or an actual kind of kinematics model just to double check things. But yeah. So
And
it's
it's
kind of like similar to like this rack, right? You saw like we put it what exactly we thought would give us good Ackerman, but then we turned it and we noticed that we like turned in front or behind, right? And so it was like the rack position actually kind of mattered, right? So that's the same thing with this. Like it does kind of matter, but it won't have as severe of a penalty as if you just made it the wrong length or you like didn't have it pointed into the center. Like that's just a kind of a recipe for having a ton of bump steer, basically.
And technically, you could move it anywhere on that line, like, and it won't affect it at all.
No.
Like,
I'm not saying it won't affect it at all. It will affect it minimally, right? Like the other two things will have. So it's with a smaller penalty than if you have to sacrifice these two, because you might sacrifice those two for your setup, right? I mean, just to get around your shock, to get to your rack to the right place. Like you might sacrifice some of these. You might not be perfect in all of these aspects, but this one I would be much more willing to make some motion in this one than I would not have it point at the instant center or something like that, or have this length be totally wrong. So I'd get the other two right, because that's gonna make very little bump steer, and then moving in and out, you might get a little bump steer, but probably a amount you can live with, basically.
And in and out, like, so if I moved it left or right, it'll be like the same amount of air.
Yep.
So Chris, you're saying that the tie rod should be about the same length as the two A-arms?
Yep, exactly.
So then we might have to have an extra link between the tie rod and the rack?
No, I think it should. I mean, you could extend your rack. Like if your rack is just really short, like let's say your rack isn't actually long enough, you could have an extension on your rack but they can't rotate about the end of the rack. It has to be like a solid extension of the rack, basically.
That's what we're gonna have to do.
Yeah, and you usually do it with rod ends. So you put two rod ends in the end of the rack, and then you can move your rod ends on the end of your rack in and out a little bit. So that can give you a little play. But yeah, so you're kind of last time we were messing around with the geometry, we were getting to mess around with the rack length. You can't really mess around with the rack length that much, to be honest, because it's going to be your bump steer is going to control a lot of your rack length, basically. Because this position where it mounts is so fixed, so you make up the difference in where you modify your rack length. You don't like modify where you connect out here, because that determines too much of your bump steer stuff, or sorry, too much of your Ackerman geometry.
And then the frame would affect it too, technically.
Yeah, I mean, it can't run into a frame tube member, right? So where you put this thing forward and back, you probably also don't want it sticking way out of your frame. I mean, you can, I guess, but
our frame was at 19, and then our rod is like 18 or 17, so
it's shorter.
Yeah, it's smaller than the
Yeah.
frame.
Well, you don't want smaller because then it's probably gonna have to hit one of the tubes to go out to your tire unless it's like very parallel, to the ground. Depends on the angle, right? But like, for example, this tie rod might hit your frame if your rack's too small, right? So,
Mhm.
so yeah, so
Yeah, we
definitely.
got a big rack.
So, and then we talked about we got a big rack. Understeer / oversteer. Right. So we talked about a little bit of steering dynamics, right? And so in that case, we drew a back tire and a front tire. And the front tire was doing a turn. And the back tire was also doing a turn, but it didn't look like it. And so this was the velocity of our rear tire right here. And it's really 100%. I can start drawing a little bigger. So this is gonna be this. And then the velocity of our front wheel was V front. Actually, it's not going to be inside. Chris, you're crazy. So here's our V front. And so this angle here is our slip angle. And so we knew that, and here's the slip angle of our rear. And here was the force in the rear. And here was the force in the front. And the force was equal to the cornering stiffness of the front times the slip angle in the front. And the force in the rear was the cornering stiffness of the rear versus the slip angle in the rear, right? And the cornering stiffnesses had to do with the tires, right? So that was, if we plotted the slip angle versus the lateral force, it was the slope of these lines, right? So the slope of these lines are the cornering stiffness, essentially, right? So the more slip you get, the higher the force is going to get. So for an oversteer vehicle, so whenever you have like alpha in the rear greater than alpha in the front, so that basically means that the slip angle in the rear, like I drew now, is quite a bit bigger than the slip angle in the front, which is common for our cars. You're going to get oversteer, and that's typically due to, one, the CG is near the rear. So to have larger forces, so this basically means force in the rear is larger than force in the front in that case, right? So this is force in the rear and force in the front, right? And so to have a larger force in the rear, because the CG is closer to the rear, you need a larger slip angle, right? Because the cornering stiffnesses are pretty similar. The other thing that can do that is if you have more weight transfer in the rear. Which also typically happens in our cars because our rears usually have we have a little higher ride frequency in the rear, and it's heavier, so our springs are stiffer, and so more of the weight transfer happens in the rear than in the front. So so that'll also cause this, and if you have like less cornering stiffness, I guess less cornering stiffness. So like let's say your rear tires have a lower slope, because your tire pressures are different, or you use a different tire in the rear, or they have a different temperature or something, right? So if this cornering is lower, then to get the same force, you have to get a higher slip angle. And so what basically ends up happening is, so whenever this happens, oversteer results. Basically, and that's from your rear going into a larger turn radius than front. right? And so what basically does is that, so the car will kind of like turn, so the car will turn in a, so the car will, um, so basically, if you have like some Ackerman setup, or just let's just say from your, you expect from your like tire, from your like from the geometry of your car and tires, right? Like, you know, based on what you predict from your tires, you know, you might predict you're going to turn around this point right here, right? But because dynamically you have a larger slip angle in the rear than the front, you're actually going to be turning around a tighter turning radius, basically. And your front is going to kind of go in, it's going to dive deeper into the turn, basically. So your front's diving deeper into the turn. And this gets worse. This gets worse the harder you turn. Right? So you imagine like up here, you know, if these forces start to get larger and larger, the difference between these two also is going to get larger and larger. So you're going to oversteer more and more. So we kind of talked about how you like the drivers complain a lot about like oversteer or understeer. That's just like you imagine oversteer, you're going into a turn, and as you're getting to the pinnacle of the turn, your basically car keeps going in more than you want. And so you end up kind of like thinking you're on your line, and you keep having to back away from it basically because your tire's pulling you into there. So that was kind of what we covered in terms of steering, right? And so to correct for some of this, you typically have some anti-roll bars, or you mess with your shock, or you mess with your shock setups, like the stiffness of your front versus rear shocks, or your tire pressures front and rear. So typically on the track, you actually will want to adjust to get closer to neutral steer. So that's one reason why you might just have one anti-roll bar, might be so that you can just adjust the relative stiffness of the car in the front versus the rear, so that you can tune in kind of a more neutral steer car. I mean, I don't know if we're there yet, but that's like what a race team, I mean, you need some on-track adjustment of your kind of neutral versus over or understeer. And a roll bar is kind of the quickest way to do that, right? And that's because it can really affect, you can't really move your CG around that much, right? But you can affect the weight transfer. Like, do you have more weight transfer in the rear or more weight transfer in the front? So that's the easiest thing to do.
Because when you see these guys like in NASCAR, where they go out to the car and they make an adjustment in the rear corner, either rear corner or the front, what are they actually adjusting? The any sway bar? Or?
I don't know, to be honest with you. My guess would be they're either doing like, yeah, an anti-sway bar, and they're usually you can adjust the moment arm of the anti-sway bar. So that's like the kind of common adjustment. I would doubt they're changing like the toe of the tire or something. Like, you might be seeing one tire get too hot, you know, and thinking it's out of alignment compared to the others, right? But I think it's hard for me to imagine that they would be able to adjust like kind of an alignment like that on the fly, basically. I would think it would be from driver response, basically saying, hey, make a quick stiffen up the front or the rear. But I don't know, to be honest with you.
I know that the shock absorbers are such a big deal that they have guys on those teams that specialize in nothing but shock absorbers.
Yeah, I mean, because if you could modify your shock absorber stiffness, you could also adjust this with your shock absorbers instead of an anti-roll bar too. So that
have
would
the
be,
double shocks.
what do you mean by double shock?
Or I mean, like, wherever the first shocks connect and the push bar, that triangle piece, what is it called?
Oh, like the rocker?
Yeah, they have like a mount for it, but they use like shocks on that, and they might be like parallel with the car, and then they have that piece, and that's just, I guess, another adjustment for something.
Yeah, like are they modifying the motion ratio because they're modifying the
I'm not
connection
sure.
to
I've
the
seen.
rocker? Because that's an easy way to adjust your spring is if you have a
It's just like the mounting point for the
yeah.
high connection.
Yeah, but basically if you have a rocker and it's connected to a spring, you're basically changing the motion ratio. Like, so for example, like if you, so let's say you have a rocker, so it's gonna basically look like this. And you have like a spring,
Oh, okay.
right? And I should draw the spring. Usually the spring you'd have a rocker, you'd put your spring inboard. And so like if your push rod connected here versus connecting here, it would have to travel very different amounts to compress your spring the same amount. So you imagine if you rotate this from here to here, the travel from here to here is very different from the travel from here to here, right? So this one is a stiff spring, so K is high. This one's like a soft spring, like K is low. It makes it seem like that because this one you travel and you compress the spring a bunch. If you connect it down here, your spring don't travel so much. So that's how you mess with your motion ratio with like a rocker or something. So Powertrain, we're 40 minutes late on Powertrain. So, so first thing you're thinking about Powertrain is probably maximize the engine power and the range where it makes that power. Let's say range in operating conditions. So that's one of your first goals. Baja don't care so much about that, but and then for drivetrain, so that's kind of the engine power unit type folks. Drivetrain wants to maximize the time when operating near peak power, right? So your powertrain should be designed, your kind of drivetrain should be designed to keep your engine operating near its peak power point, right? And then it should also, if they get any say in the tires or some geometry, they should be maximizing the tractive force of driving wheels, right? So, I mean, that's why we kind of started off with just basic dynamic and stuff at the wheels, basically, because any decision you make on the car its influence has got to be done through the wheels, right? So it's kind of the gatekeeper of any decision you make. So in the end too, they should be pushing for, and you have these other goals, right? Which of course are like reliability. This thing can't break, right? You probably want it to be drivable by your drivers. Right? I mean, so you drive some great car, but it's too complicated for any of your drivers to drive. It doesn't do you any good, right? And it, better integrate with the vehicle and suspension. But vehicle suspension and dynamics, right? So like, I don't know, kind of an example of that would be like the Baja team, they drive with a U-joint. So that's actually one of the kinematic links of the rear suspension, right? So anything they do is drastically affecting the rear suspension. Or like in the Formula car, they want to run a double wishbone suspension, right? Which basically means you cannot run a U-joint for that type of suspension. So the drivetrain is kind of forced to run a CVE, something that can allow for a change in length of their drive shaft, basically, which like their plunge. So you got to keep those in mind. And we're gonna talk a little bit about the engine. So we're gonna do kind of the bill plot. So the cycles of the engine. So this will be kind of a review if you were there for talking about the engine, cycles of the engine. Right, so this is gonna be a 4-stroke SI, so that's spark ignition. Right, so we're gonna be talking about 4-stroke spark ignition since that's what we all use. Oh man, how can we continue without Juan? Just kidding. So we're gonna start off with the intake stroke, and we're gonna draw the engine. So we have our spark plug, and then we're gonna draw our little valves in here. These are supposed to be valves. Should kind of be bigger. So right, and then here's our cylinder wall, and then here's our piston, right, and then the piston, and then here's your crank, right? So we'll say it's coming up about around here. And here's so that's our crankshaft. This is our connecting rod, right? And so this usually starts around 0 degrees and goes to about 180 degrees. And so that's when it goes from the top down to the bottom. So this is like, close to top dead center. So when it's up here, this is when it's at like top dead center. And so we can also draw this on just kind of so this is your crank angle, right? And so we'll say this is intake valve will be open. And so let's break this up into 180, 360, 540, 720. So that's 2 revolutions. So your intake valve will be open this whole time, and it's going to come and it's going to close right here. So IO will be intake valve open, basically. But I should do it this way. So typically you say like IC. So this would be like IC. So intake valve closing. So that's like the moment when the intake valve closes, right? And this is intake is open. It's open this whole time. And it opens actually right before 720. Right? So it kind of comes, and this would be 0. And this would be top dead center. So top dead center before the intake stroke. And so it's going to come down. So I should let's redraw so my intake valve should be open, right? So if it's open, it's going to push into the cylinder. Maybe not this far, but it's going to push in, and that's going to allow air to flow in. Right? So there you go. So and that's going to go, and as it goes down, it's going to go 0 to what we call 180 degrees. And that's because this crank has basically rotated from top down 180 degrees down to the below. And then we're going to start with the compression stroke. Compression. Right? And so we have still have our spark plug. But in this case, our intake valve will close at this point. Right, and it'll be, right, and so this will be coming back up. And so coming up. And so now it'll be going from 180 degrees back up, and it's going to go to 360 degrees with it traveling back up. And these are all closed, right? So this is basically intake in this area. Is what we roughly say. Here we call this compression, right? And so once it gets back up to about 360 degrees, you're going to have your spark. usually a little before top dead center. So here's your spark. And that's usually at the start of your power stroke or your expansion stroke. So we have power or expansion stroke is what we call this. So it comes down, closes. So both valves are closed in this instance. So now it's going to start coming back down. And at the start of this thing sparked. Right? Started the flame propagation. And so this is rotating this way, of course. This is rotating this way. So it's going to kind of come back down to something similar. Right, so there's the crank arm. Here's your connecting rod, rotating back down. This is traveling back down. So this is going to go from 360 degrees to about 540 degrees during the power stroke, right? And so this is where you're getting all your power back out. So this is your power stroke. And then at about right before 540, you're going to get your exhaust valve opening. And it's going to stay open and it's going to overlap slightly. And I should call this point is your intake open. And at this point, this is your exhaust valve closing, right? And so there's some valve overlap and that gets larger. Well, it depends. You can have variable valve timing, right? So a lot of times this timing is all fixed because it's all a mechanical linkage. But if you unlink it mechanically, you could start to like increase your valve overlap at higher speeds and that sort of thing. So this is your power stroke. And then this was your exhaust stroke, right? Roughly here to here. So in your exhaust stroke, you have your spark plug, you have your intake valve, but your exhaust comes in, right? And this piston is now traveling back up. It's going to come back down. And then you're going to have your connecting rod. And so this is going to go from 540 degrees up to 720 to end the cycle. So one thing you should keep in mind is every full cycle of the engine, you get 2 RPMs, right? You had to rotate your crank twice for every time you did a cycle you did all 4 of the kind of cycles of your engine. Or I guess the 4 strokes of your engine. So in this case, you have your exhaust is kind of coming out, right? And you want to get all your exhaust out. So for like a fuel injection, right? You typically inject somewhere here. So you might like inject fuel in the manifold. So because you're injecting fuel in the manifold, you can actually, which is like up in here. So that's like towards the end here, right? So you're kind of injecting fuel into here. This is fuel. Because the intake valve's closed, you can do it a little bit early and let this kind of mix before it comes back around to the cycle where your intake valve opens. If you're going to inject fuel into your cylinder, you obviously do not want to be like injecting fuel right before the exhaust stroke, right? Because you eject it in and all your fuel just get pushed out your exhaust. So basically you have to wait until your exhaust valve closes and then you can kind of inject fuel. And you might even wait till longer. So that's kind of the, and so basically a lot of your engine components are basically designed to get all this timing right, you know, and to be able to modify this timing as needed based on engine parameters, you know, exactly when is your spark going off, exactly how much fuel's coming in. That's all being modified by your engine, either by your carburetor and distributor or some electronic control unit, basically. So if we're engineers, which we are, we like to plot things. And so we like to plot this on what's called the PV diagram. Okay, and so when we're gonna have some different phases. So here we're gonna have the volume at bottom dead center. And here's the volume at top dead center. Sorry, top dead center has the smallest volume. Volume at top dead center, and here's the volume at bottom dead center, right? And so the difference, between those two, volume at top dead center and bottom dead center. So if we kind of drew some lines here from here to here, this is the stroke of our engine. So the difference in the height, how tall, where the piston's at top versus where it's at near the bottom, that's your stroke, right? And then the volume displaced is equal to your stroke times the area of your piston, right? And the volume at bottom dead center, or sorry, the volume at top dead center is this little head volume in here, right? So you can design for that. And if you wanted to like decrease it, right, you could like you could have like a hemispherical piston head, right? So that'd be one way to decrease that value if you wanted. So how this works, so what it looks like, right, is you start off at 0 degrees right here. Maybe I'll draw it in black and I'll say this is 0 degrees. Let's do that. So this is 0 degrees. It's gonna be blue. No. 0 degrees, start of the intake stroke. Sorry, I can't make up my mind today. So we do our intake, and our intake is going to go from 0 degrees to 180 degrees. So that's our intake. And then what's going to happen is our intake, and so basically we are at one pressure, kind of at our inlet pressure, and we were sucking it all in, and now we're full of air, right? So next thing you do is we close it off and we shrink the volume, but in this case the pressure goes like way high basically. So so we'll do blue. We can do green for the compression stroke. So you're going to get kind of this behavior, right? So this is your compression, right? Your compression stroke. And then you're going to spark it. Boom. You're going to get some big increase. Hopefully you left yourself a little more room than I did. Somewhere here, something like this. And this is the spark. So you get this huge increase in pressure at this fixed volume. And then you basically get your expansion stroke. So what color do I want to be? We can do power stroke. Then you do your power stroke. So yeah, it's not really a very good shape for it. This is your power stroke, right? And then you have your exhaust stroke. So your exhaust goes from here to here, here to here. So that's 0 to 180. This was 180 to 540. This was still at 540. This came 180, sorry, to 360. This is 360 degrees. This was 360 degrees, right? And then this came down to 540 degrees, and this went to 720 degrees, basically, right? And then you go from here to here. Start to exchange the gas. So does anybody remember when you go in a clockwise fashion on a PV diagram, what does that area tell you?
Is it work?
Yeah, work, good or bad, good work or bad work?
I want to say good.
Yeah, it's good. So this is the work out. So this clockwise area, so this direction where we're going clockwise, this area is work out. In this case, when you're going counterclockwise, this is work that's input. So this is, so you basically, on your PV diagram, you want to maximize this right here. So this is going to be your P inlet, basically right here. This is your P exhaust. right? So area, well, let's just say work net is going to be equal to work out, which is upper area, minus work that has to go in, which is lower area. And this is also known, AKA pumping work. So one common metric to compare engine performance, what you typically do is you take these PV diagram and you take that work, this net work right here, and you'd be curious, basically, usually this P ends around atmosphere, and then you have your V top dead center, V bottom dead center. And this value right here, P, why am I blanking on, what is this called? What's IMEP stand for? Control find.
Pressure? Is it internal mean effective pressure?
Yeah, internal mean effective pressure. Thanks, Rafa. So this is internal mean effective pressure. I think that's what it is. It might not be internal, but could be. But anyways, what people name it doesn't really matter. This just has the net work in here basically, right? So this pressure right here, it's kind of like normalizing for the volume of the engine so you can compare it to the other engines. So like, so the net out is going to be equal to your volume displaced times your pressure IMEP. Right. So this is this distance right here. Usually you put this at like 1 atmosphere. Right. So you give a pressure reference to atmosphere basically. So it's basically this distance right here. And this is nice because you can see like it's basically you take the network. So we can see that PIMEP is equal to the network over the volume displaced. So it's basically, it kind of tells you like how good are you doing, irrelevant of how big you are, right? It kind of normalizes. So if someone's got a really big engine, you got a small engine, it's like, of course they're going to have more power output, right? Okay, so it's it's a good metric, and you'll see we might use it later. So what do we want to do, right? We talked earlier. So we want to increase power. Power out. So like basically increase W net, increase the network. So our kind of first option to do that is to have more air and fuel. So the more air and fuel you can burn, the higher you can spike this pressure up basically, right? So if you can get more air and fuel, that's better. And so to do that, you can
I had a question, Bachman.
Yeah.
What does it say in blue on that PV diagram above? It says 2 something.
So it's just, this is 1 atmosphere. So like usually like the
I
inlet
see.
pressure, you say it's like 1 atmosphere, right?
Okay.
And then, so this pressure is just reference to atmosphere, right? So if you're at 1 atmosphere here and you say this is 10 atmospheres, that's basically saying that's basically saying that the distance, this is usually gauge pressure.
Okay.
I believe actually. I should actually check that. But so I think it's kind of referenced to the inlet pressure. So it's the height from here to here basically. So it's basically this height. It's not from the ground, kind of the ground up. It's the height of this it's the height of this, right? And so you could kind of put this at the inlet pressure around 1 atmosphere. All right, so the more power you get means you basically want more air and fuel, right? Which you can improve air intake. Right, so if you can make your valves bigger, right? If you can have less restrictions here, right? If you can force air in during the intake, that'll help you. That can help you do that, right? So you improve air intake, improve removal of exhaust gases. Right, so we kind of went through the PV diagram just for Bill. So you come in and you push up and you push out all the exhaust gases, but the piston head can't actually go all the way up and clear out the full cylinder. It actually leaves a little bit of residual gas inside the cylinder every time. And that gas, dead burnt gas, basically, it has no oxygen in it. That'll basically take up usable volume of what you could suck in fresh air with, right? So if you can improve the removal of your exhaust gases, you can, you want to do that, right? And that's make your valves bigger, improve your valve timing, get your exhaust flow to have as little restriction as possible. We've even talked about using some resonance effects. I'm not going to talk about that today because it's too deep, but it's in the handbook. All right, so we can force air in. Talked about that, and we can increase the density of air by making it cold. I mean, these are just kind of a common list. There's, the engine's about as complicated as the whole rest of the car almost, right? Probably an actual design. So another thing you can do to improve your kind of power output is you can decrease your pumping losses. Right? So we talked about how to decrease pumping losses. So we talked about how we take the intake air in at a lower pressure than when we push the exhaust gases out. So that actually consumes power basically because we have to push exhaust gases out at a high pressure. So if you can decrease the area of this little rectangle, then you can increase your net power out of your engine. So I mean, common ways to do that is to increase the inlet pressure basically, right? So if you increase the inlet pressure by like using a turbo or supercharger, you'll actually flip these pumping losses. So decrease pumping losses. The other thing you could do is you could suck the exhaust gases out with like a vacuum, but I don't think you typically do that. So we decrease the pumping losses, and that's usually through like a turbo or supercharger. Or we can increase. So if we can increase this max pressure up to here so more air and fuel gets us a higher spark. We can increase also where we get for pressure in terms of this green, and that involves increasing. So increase pressure before spark. So that involves increasing the pressure ratio or compression ratio. Right, and so your compression ratio, we'll say R, is going to be your volume at bottom dead center over your volume at top dead center. Right, so that's basically how much do you compress the air basically, right? So it's the ratio of this volume to this volume, and you want this to be as high as possible. That's why race engines, they'll push this up, up into the 14, 15 range, maybe even higher. And then like your typical passenger vehicle won't go to those higher pressures. They'll be down in, 10, 12 range. More air and fuel. The one thing I left off there was increased displaced volume. That's the kind of American way. Why mess around with the little stuff? Just make it bigger. So yeah, so those are kind of some of the ways you can get more out of this power out of your engine. So let's look a little bit more at something else you can do. You could try and improve the combustion. Right, so first things I should say about the combustion is that the mass that you actually have to burn of air inside the cylinder is going to be equal to the volume at, let's say, usually you put it around the volume displaced, because you assume that you can't get the full volume at bottom dead center. Like ideally, right, you go all the way down to bottom dead center at the end of this stroke, and then you'd have a full cylinder. But when you pushed it out, you actually had some left unburnt gases. So typically you're going to say you can bring in air at that volume times the density of the air at the inlet times, usually you multiply that by a volumetric efficiency. So a really good engine, you're going to completely refill the steep displaced volume with, well, I guess we can, this is actually just the density of air at STP, standard temperature. Because this actually corrects for having bad densities as well. But basically, so if you're, if for some reason you get your air too hot or something as it goes in your engine, you'll take a penalty. But this is basically how much air can you fill in your volume that you're taking in. So, if you got a 5-liter engine, and so maybe each one of your cylinders is 0.8 liters. When you suck it in, are you getting in 0.8 liters of fresh air? So you take this air and you burn it with gasoline, roughly this. And what you're going to end up with is you're going to end up with mostly water and carbon dioxide. So you can basically see, so for every molecule of gas you put in, you need about 12 molecules of oxygen, right? So the more air you can get in, you can put in, more gas, right? So that's why the name of the game is get air in there. And so your air fuel ratio, and so this is at stoichiometry. So we call that stoichiometric. So the ratio of air fuel at stoichiometric by mass, right? So this would be 12.5 to 1 if you count like by molecules, or if you said like by moles of molecules, but we just do it by mass since we like to work in mass. It's typically around 14.7. So that's unitless. And so if you have an air fuel ratio in your cylinder that's higher than the air fuel ratio of the stoichiometric one, that means you have more fuel in. So that is you're burning what we call lean. And so when you're burning lean, one, you're going to burn hotter. You're going to have more fuel efficiency. So that's an ADA fuel. So you're going to have a higher fuel efficiency because you're burning all of your fuel.
So Bachman, question.
Yeah.
Why is it that the general consensus is that you make more horsepower when you're running leaner, when you're burning all of your combustibles, versus when you're running richer, when you still have the potential to combust the fuel that's inside? Does that make sense?
Yeah, I mean, my intuition, and so far anything I've ever seen, is the opposite though. That you want to run your engine, if you're like running a race engine, you should run it slightly rich, because otherwise it's like you're limited by how much oxygen you can get in your engine, right? So you might as well dump in a little bit of extra gas to make sure you burn up all of that oxygen and get as much energy out. If you don't put in enough gas and you just run lean, basically you just wasted oxygen in your cylinder. So for example, this is gonna have I think slightly less probably peak pressure because you're not gonna burn quite as much. But since you burn hot, you form more NOx and sulfuric oxides and that stuff. So it's actually, usually it's worse for producing these kind of pollutants. That's my understanding, Colin, as far as I've ever heard. And that was like looking at AEM and stuff and the tunes. You typically run a slightly rich air fuel ratio. It might be, I think you run more, and there could be second order effects about these sorts of things too. But that's as far as that's everything I've seen always basically says that you should run slightly rich if all you care is about power output and you don't care about hurting the environment. So in this case, you're going to run a little bit cooler because you have more, so you run a little bit cooler. What's a good way to explain that? So you don't quite burn all of the fuel, and so you have some fuel kind of going along for the ride that just have to heat up, and so that'll help absorb heat. So run a little cooler. You're gonna have lower fuel efficiency though, because in this case you're pumping in a little fuel that didn't get burned, so you're wasting your fuel in this case. But so that's not good. Plus, but you're gonna have usually higher pressure. You're gonna have less NOx and sulfuric oxides because you're colder, but you're gonna have more particulates, and because those are made of carbon, unburnt, not like partially burnt carbon, more particulates and unburnt fuel. So I think so controlling this is, controlling the temperatures and stuff are very critical for pollution, but we're a little less worried with that, I guess, than
Chris?
Yeah.
I think the term you want to use is not richer, but less rich, less lean. You want the engine to be as lean as you can make it without doing damage to the engine, because if you get too lean, you can burn valves, right?
Yeah, if you get too hot.
And another thing it can do is you can detonate the engine. And detonation happens when the head is too hot, and the engine can actually blow the piston up, crack the head, do a lot of serious damage. So you want to make it as lean for power. In fact, the old aircraft engines, they used to have a setting called lean best power, and they would watch it as they leaned it out, and then when it got too lean, or at that point, they have what they call a torque cell on the engine. They could see how much power the engine was making, and then they just back off or increase the mixture a little bit to make it a little richer, just to save the engine. So lean best power was the optimum setting for the fuel mixture.
Interesting. Well, I'll look into it a little more next time, just to look at what is the exact air fuel ratio you'd run relative to stoichiometric. And we can look it up here if we have more time. And Bill brings up a good point about like auto detonation. So if things get too hot, or you run compression ratios that are too high, which also things heat up a lot as you compress it, but your fuel will get so hot that it'll explode without the spark, basically. Or it'll also it'll explode before the flame from the spark reaches there. So what that'll end up doing is basically, one, it could explode too early, which will, obviously send huge forces through the engine when they don't want to see them. But a little bit of knock is usually just because it's in the exhaust stroke somewhere, but the flame front hasn't hit it yet. But that's not good either. It'll tend to break things. So yeah, usually there's little sensors on the car now, little microphones, and they'll listen to that. let's see here. I might have some charts on this. So let's see here. So here you can see, so let's see here. So here you can see the fuel air equivalence ratio at 1. And here you can see the effective, the internal mean effective pressure. So this is going to be related to your power output. So having a fuel equivalence ratios slightly close to 1 will typically be highest. But you'll see here these dashed lines. These dashed lines are for real engines. And you can see, so the highest is usually slightly higher on the fuel than air. It's a little higher than 1. So yeah, so I'd say you tip, at least the data I've seen, let's see if I have any other, is yeah, you definitely don't want to run too too rich, but yeah, especially I think as you get leaner and leaner down here to stoichiometric, you're going to get hotter and hotter. So yeah, so you probably, and it's probably a trade-off of efficiency too. So let's see here. So here's fuel efficiency versus compression ratio. And I'd have to look at this a little bit more, but you can see kind of like, and some of the confusing parts about this is people use different equivalence ratios. So I typically use what's called lambda, but not everyone does that. So let's see here. So air fuel ratio equivalence. And so usually you say this is lambda, and that's going to be the air fuel ratio that you're actually at compared to the air fuel ratio when you're stoic, when you're at stoichiometric. But they also, this is different from phi, the equivalence ratio of phi, which is 1 over lambda. So it gets kind of confusing, but for lambda, if lambda is less than 1, it's rich. And if lambda is greater than 1, it's lean, basically. So if we look a little bit at fuel efficiency, we can see some of the things that kind of matter. So for example, so if our fuel efficiency is kind of the work that we get out, so our net work out, over how much energy we put in the fuel, so that's the mass of the fuel times Q, we call this lower heating value. So this is the energy in the fuel. So that's the fuel efficiency. And we know that the power of the engine is the net work times, we should call this net work times, let's say, I'm just going to say RPM. The units aren't quite right, but over 2. So there's some factors in there for the units. But so if we put in, so the net work here is going to be equal to the fuel efficiency times the mass of the fuel times the lower heat, how much energy is in the fuel. So if we put that up here, we're going to get the fuel efficiency times the mass of the fuel times the lower heating value times the RPM over 2. And the 2 just comes from the fact that you do 2 revolutions. Anyways, well, this power is going to give you a weird unit at least. So if we want to, we also know the mass of the fuel is going to be the mass of the air that you get in divided by the air to fuel ratio that you have, right? And we know the mass of the air, sorry, not m dot. We also know that the mass of the air is going to be equal to the volume displaced. The volume displaced times the density of air times the volumetric efficiency. So I'm just going to plug those in. So the power of our engine is our fuel efficiency times our volumetric efficiency times the volume displaced times the density of air times the energy density of our fuel times the RPM over 2 times the air-fuel ratio. Oh, sorry guys. Sorry about that. So basically I put in M fuel, I put in M mass of the air up here. So we have volume displaced, density of the air, volumetric efficiency, how well you get air in and out, and you have air-fuel ratio on the bottom. So here you can basically see if you want more power, 1, you increase the RPM, 2, you increase the energy density of your fuel, or you can increase the displacement of your engine. You can increase the volumetric efficiency of your engine by getting air in and out better, or you can increase the fuel efficiency of your engine. Usually that's done by increased compression ratio. So increase volume bottom dead center over volume top dead center, right? So that's your compression ratio. Right? Or you can decrease your air to fuel ratio. I mean, within certain limits, basically. So yeah, so that gives you, and we also know that, so if we just want to put in this net workout is just your internal mean effective pressure times your V displaced, right? You could also just say this is P, your pressure, mean effective pressure times volume displaced times RPM over 2, right? But anyway, so you can see some of the knobs that you have kind of at your disposal for the engine, and what this actually turns out to, what an engine. So this is someone who's like super into engines, right? But typically as a designer, what you actually, the only thing you kind of, if you're not making the engine, what you really need to look at is the torque versus RPM curve of the engine. So our torque versus RPM, and this is our RPM max, let's say. So we have these two limits. We're typically going to look something kind of curved and then kind of drop off, right? And so here's your peak torque. So here's your peak torque basically, and here's your RPM at peak torque. And if we know that power is going to be torque times omega, right? Typically you'll see like power equals torque times RPM over 5252. So that's only when you want power and horsepower, torque and foot-pounds force, and you put in RPM and RPM, right? So this 5252 does that conversion, but typically it's your torque times your omega. So you imagine it's basically this torque times the RPM. So basically it gets higher and higher. It starts really low because you're multiplying by a small RPM, but out here you get a lot more power for this torque because you're multiplying it. So it'll typically run something like this. Right, and so this will be, let's say this is your power. There you guys go. All right, so your power band, right? So here's your peak power, and then here's your RPM where you reach your peak power. Those are supposed to line up. So here's your power band. It goes from like usually your peak torque to your peak power roughly, and that's just roughly what we call where you have your high power, because you see it starts to, as the power drops off, as your torque drops off after the peak torque, this power curve will usually start to flatten a little bit basically. And so you basically want to ideally keep your engine running in this area in order to have kind of peak performance. So that's how we segue into the drivetrain. So drivetrain goal is to keep engine.
Question, Bachman.
Yeah.
Why do you think the torque starts at a higher value than the power? You see how
So,
my
like
bad.
these difference right here?
Yeah, like why do they have different starting points?
I mean, so keep in mind that typically you'll plot them on different axes. So you can totally mess with how these look
Yeah.
based on how you scale your power axes versus how you scale your torque axes. Because otherwise they're going to be like, right? Because you imagine like, I mean, I guess they're okay if you put it in horsepower and foot-pounds force.
Yeah.
But if we just like, you know, most are, let's see here. So most of the time you'll see you'll have your power on the right and your torque on the left.
I see.
And so it's like comparing them like is not really, it's more you're looking at the kind of you're not really comparing them too much. You know, you kind of know the power curve you can get directly from the torque, and you can manipulate kind of how they look compared to each other if you change your axes basically.
I see.
Like if you made this 0 to 1,000, this power curve would just look really low down here, right? So it would look very different.
I see.
So yeah, so don't worry so much about the way they look relative to each other. It's more about kind of the shape and like how much peak power are you making, and like where is your peak torque happening, and this kind of having this high peak power across a range of RPMs basically.
So when you're driving, you want to generally keep it in that power band then, huh?
Exactly. I mean, if you're trying to go as fast as possible, right? I mean, you're driving around town. I don't think you need to keep it in the, you don't need to quite keep it in the power band.
All right. Thank you.
No problem. So so now we get into drivetrain a little bit. So let's draw a very simple drivetrain system. So let's say you have your engine has an output shaft and it's rotating. So it has some omega of the engine spinning at a certain rate, and then it has also some torque coming out of the engine. And that comes back out to some sort of other, you know, this could be a gear, it could be a sprocket, right? So we'll zoom in on this. Come on, zoom. So, you know, we'll say this has some R1. This has some R2. Right? And then we'll say this. So you have your engine, it's running this. So this is kind of has some omega 2, has some torque on 2, right? And this is going to be driving some wheel. Right? So this is your tire. So, and then you have some here, you have some radius of your tire. Right? And basically your tire, you're moving at some velocity, and you're doing that because you're essentially applying a force. You're pushing backwards on the ground, which I should kind of say. So these are some force on the ground. Right? So our question here for setting up our drivetrain, it's kind of, all right, how do we compare this? So this is angular velocity. So this could be like RPM. But typically we work in radians per second just because the math is easier. But it could be, you can kind of just consider it like RPM. It has to do with how fast it's going, how fast it's spinning. So how do we compare the RPM of the engine to the velocity of the car in this case, right? So one thing we should know that we can call the ratio of R2 over R1 in this case, we'll call that our gear ratio of our system, right? So this has a a larger radius back here than here. So we have like a gear ratio maybe in this picture of 4 to 1 or something. So I know that the velocity of the tire is going to be equal to the radius of the tire times the speed at which the tire rotates. I know that the speed at which the tire rotates is equal to the speed at which this sprocket or gear 2 is moving. Right? So I have this sprocket or gear 2 is rotating. They're rotating together, they're fixed. And I know that omega 2 is going to rotate at the speed of the engine divided by the gear ratio. So that basically tells me that if I want to, I plug in these into here, and then I plug those into here, and I can find the, I can find the, and then well, actually no, I'm going to go the other way. I'm going to plug this into here, and then I'm going to plug this into here, and then I'm going to get velocity. It's going to be equal to the radius of the tire times omega of the engine over the gear ratio. Right, so that's how we relate the velocity of at which the car is going to the velocity at which the car is going to the radius of the tire and the gear ratio. And we can do the same thing. We can go from the torque of the engine to the force on the car. So, for example, like the force on the tire, so we'll start at the tire again, is equal to the torque on the tire divided by the radius of the tire. And I just can remember that because I know torque is like a pound times distance. And so I need to divide by a distance to give me, so it's like I got force times distance. I got to divide by a distance to give me my force. And then I know the torque on my tire is going to be equal to the torque of my engine times the total gear ratio that we're going to see. So I'm going to do the same thing here. And I find the force on my tire is equal to the torque on my engine times the gear ratio divided by the radius of my tire. And what you'll notice if we put these two things together, the torque of the engine, like if I just multiplied these two equations together by multiplying the right-hand sides together and the left-hand sides together, I would get torque of the engine times the speed of the engine is equal to the force on the tire times the velocity. And this basically is just the power is conserved. So the power out of the engine is torque times omega. The power you're putting out into the ground is force times velocity. So they're going to be the same, right? There's no, there might be some drivetrain efficiency losses that we're not taking into account in this case, but just in general, energy is going to be conserved. So if you put energy out through your engine and connect that to the wheels, then that's going to, then those are going to be the same. Let's get back to viewing this at 100%. Okay, so how do we usually think about this? So usually what we're going to do is we're going to plot omega, right? And if we want to convert RPM to omega, we have revolutions per minute of our engine basically. We can multiply that by every minute has 60 seconds. And then every revolution has 2 pi radians. So that's like 6.28. So basically this is around 6.2. This is 60. So you basically got to, so like 100 RPM is like 10 radians per second. And this is of the engine. So if this is omega max power, we want our engine sitting at this power the whole time. And let's plot this versus the velocity. So if I'm sitting in one fixed gear, what's the ratio, what's the relation that I'm stuck on between velocity and omega? Well, I can see up here, I can see up here that my velocity, the slope of velocity over omega engine is going, did I do this right? Oh yeah, no. So omega engine divided by velocity is going to be gear ratio over the radius of your tire. So these, I'm stuck to straight lines depending on different gear ratios, basically. So you might call this, so the slope here is the gear ratio over the radius of the tire. And this might be like first gear, second gear, and third gear. So what'll basically happen if I have omega idle, so this is like the speed at which I'm idling at. Basically what I'll do is I'm gonna use the friction in the clutch to go from idle over to this velocity, right? It's like I'm not even in first gear. So this whole time is basically just rubbing the this whole time is basically either rubbing the clutch, or you have that torque converter, which is like kind of a hydraulic mechanism in an automatic car. And then you're gonna ride first gear all the way up to here until you're too high of an RPM, you're getting away from max power, that you need to drop down to your second gear. And then you're gonna ride second gear, and you're gonna start below max power, go above it, and then you're gonna drop back down. So this is if you have kind of a geared system. So this is like an FSAE system. So Baja uses a CVT. So ideally Baja will shift in. They're gonna come here, and then they're gonna shift along this max power until they reach their high limit, and then they're gonna come up here basically. So this is like Baja, ideally. So because they have a CVT, that's kind of the use of a CVT. It lets you sit right at that max power that whole time, you know? So let's do some let's pencil some of this stuff out here a little bit. Right? So you're basically, so when you're a geared car, you're basically forced to go along these lines as a function of velocity. And you could see here, this could tell you when to shift. So let's go back into this old document we were working on. Let's see if we can do some stuff with it. So remember, we were kind of doing before, we were kind of looking at different speeds, and we were trying to, for different, I gotta move this, there we go. So for different speeds, we were looking at like low speed, we were traction limited by this acceleration, right? And then we could get into propulsion limited areas. So since we already have this all set up, let's add some columns. I'm curious, as a function of our speed, what is the optimum gear ratio? So let's add some stuff into this. So insert. Okay. So usually you have some fixed gear ratio. So fixed gear ratio. So like, you know, Formula, it's maybe like 3-to-1. Baja, well, they're both actually about 6. Because Formula, it has 2 fixed gear ratios. We have our sprocket, and there's inside of our gearbox, there's a fixed ratio that isn't a part of the shifting. And then we need the radius of our tire. So let's say it's 10 divided by 12. It's 10 inches. So this is in feet, and this is unitless. Right, and so, and then we also need to say, what is our RPM of max power? So if we pull up here. So here's our formula engine. Say here's 8,000 RPM. Let me make sure I'm doing this all in the formula tab, because I think there was 2 tabs. Yeah, we're in formula right now. So I'll do this for formula first, but Baja, you can do the same thing. So let's say we're before we were making it at, 8,000, we're probably making it at 6,500 RPM now. So let's pretend like we're making our max power at 6,500 RPM. So 6,500, and this is an RPM. And we'll convert this to, insert, we'll convert this to omega max power. So this is going to be equal to this value times 2 times pi. Can you just do pi divided by 60 seconds? No, you need to do open close parentheses, I think. There you go. So it's roughly divided by 10. And so this is in radians per second. Okay, so this is going to be our optimal gear ratio. Okay, so for our gear ratio, right? So if we know that our velocity is equal to our omega engine times, if we set this omega engine as the peak power, then the gear ratio, I should just draw this. 1 second.
Scroll.
There we go, baby. Now we're in business. All right, now we're scrolling. I'm scrolling on my end. So the gear ratio then is going to be equal to the radius of the tire times omega peak power over the velocity. So that's what we're going to plot. So let's check this out. So, and I have to do this in feet per second. So optimal gear ratio. So I said that was going to be equal to omega times the radius of the tire. And those two should both be fixed. They should not be changing. Divided by the velocity in feet per second. We'll go all the way down to 136 miles per hour. Okay. I'm going to confirm what the I want to confirm what the fixed ratio is in the formula car. Oh, the reason is we need to divide this. So if so for formula, it has a fixed gear ratio. How are they? There you go. 2.19. So I should say that. So, but if this gear ratio is actually equal to, like, you have your gear ratio of your transmission plus the gear ratio that's fixed. If you divide, you have to divide this gear ratio fixed across right here. So we also need to divide by our fixed gear ratio. Divide by that, divide by our fixed gear ratio. Okay, so I'm going to copy this plot and let's put it over here. Actually, I could probably put it on. I'll put it on. I'll put it on this plot. So select data. So we're not gonna do our power. We don't care about the powers anymore, but we want to add. This one is optimal gear ratio, and we want to compare the velocity in miles per hour to the max gear ratio, or the optimal gear ratio. And hopefully it plotted it on the same axes. Okay. So basically what you can see is, so in order to, so here I'm basically plotting it's on here. So it's Excel and G's or gear ratio. I don't know why this one's like, why does this have a marker? Marker. I'll make this line black. All right. Okay. So in order to have your engine at its peak power, basically, you'd see early on you need some crazy high gear ratio, right? And that's because your engine's spinning like really fast and your tires aren't moving. So you need this huge gear ratio to couple them together. And then you'd actually need to come down to over 1-to-1 and all the way down to the super low gear ratio down here, kind of optimally. You can tell, but you know, in this region, your gear ratio is maybe not as sensitive as long as you're making enough torque that you're not propulsion limited, right? So remember, this was perfect. This is power right here. This is assuming that you have a perfect gearing, basically, which you won't have. But your optimal gear ratio, right? You can tell it starts high and then it's going to get lower and lower. And that's why you'll tell when, like, for example, in the formula car, it has first gear is 2.5, 1.75, 1.33, 1.1, and so forth. So they have, you imagine they're going to chunk it. They're chunking this portion off into, you know, they have this gear for earlier on, then they have like this gear, and then they have this gear, and then they have like this gear here. So we've written a simulation which basically takes in a lot of the quantities about the car, the drag coefficient, the frontal area, density, right? So these are all stuff, you know, coefficient of rolling resistance, coefficient between tires and the ground. So we should jack this up. We know this is like 3. And then it takes into account like the weight of everything and the moment of inertia. And then it basically, so it basically runs the code for doing different sprocket ratios to see what the acceleration is like. So I'm not going to run through all of it right now, but I'll at least run the code and you can see, because Baja has one too, and it'll kind of show you some of what's going on. So let's see here. So here's where you can see kind of the RPM versus time for our engine. So you can see it idles, comes in at 2000. You can tell this one's not even high enough to spin the wheels, but it comes in here at like 2000 at idle. It comes into first gear. You stay in first gear until you get up to above our peak power. It shifts to second gear, shifts to third gear, fourth gear, fifth gear, and sixth gear, basically. And so for this run, you can see here's your velocity versus time. Here's your position versus time. And these ones are meant for having more. So let's look. So we can try and run this simulation, but we can run it for different chain sprocket ratios. So if we have, like, let's say 3, 4, 5, 6, 7, 8, and 9. So sprocket ratio, these different sprocket ratios, because on a formula car, you have a sprocket coming out of your transmission, and then a sprocket that goes back to your wheels. So what you'll see is some of these high gear ratios, like a gear ratio of 9, is able to spin the tires, basically. So that's where we're peaking out up here. You can see some of these other ones, and you can see where they shift, right? So that's the traction versus velocity, right? You can see for different fixed, because this is gear ratio is part of the fixed gear ratio, you can see how it slightly changes all the other gear ratios. But these you can see, interestingly enough, that one thing you notice is that in these cases, for example, your max speed, your max velocity, so let's look at here, position. We need to run, I'm gonna run some more actually. Let's run some lower ones. 0, 1, 2, well, 0 is not gonna make sense. We looked at this one, we looked at this one. This one. So what you can kind of begin to see here is that your final velocity at the end of this time, it kind of comes and it reaches a maximum value. And what basically is happening is in these other sprocket ratios, you aren't reaching, you're basically being limited by the, kind of max RPM of your engine. You're not being limited by the power of your engine. So if we looked like here, for example, right? So if the max engine velocity in your like last gear ratio doesn't allow you to go any faster, we can't reach the velocity that we are calculating earlier, right? So, you know, before we are calculating these max speeds based on the power of the engine and drag and rolling resistance, well, you're never even going to reach it unless you gear it right, which we're beginning to see. So you can see like gear ratio of 1, this blue one, gear ratio of 2, like they're reaching that top speed, right? But if you use a gear ratio of 9, basically you can't reach that. You're not going to reach that top speed. And you can also begin to look at, okay, well, what is, for different sprocket ratios, what is the time to reach 246 feet, which is the acceleration event, or 500 feet, which would kind of be a long straightaway? You can see that you can get in just under, 5 seconds. If you, under 5 seconds, if you have a sprocket ratio of like 4 to 5. So that's one of the other like powers of this code. So, or doing some of the simulation. So there's also one for Baja. Let's run the Baja one. You can see how it's a little different. So it takes in similar stuff, but in this case, for example, like your high gear ratio and your low gear ratio of your CVT. So this is the range at which the gear ratio can shift, your CVT can shift. And then in this case, we're going to try, we try different gearbox ratios. So let's try some of these. And you'll see kind of the difference in how the system performs.
Bachman.
Yeah.
For the fixed gear ratio, do you mean like the ring and pinion?
Or
what do you? I get confused with.
So let's see here, like
ring and pinion would be with a standard differential. On this car, our car would be the gear ratio between the sprocket on the differential and the output shaft of the transmission.
Exactly. So that's exactly right. But the other thing with this KTM transmission is it has a final drive reduction inside the gearbox as well. So inside like the gearbox,
Yeah.
there's actually a reduction that's inside the gearbox.
I see.
So there's actually an arc. So there's the gears that are meshing and unmeshing, but there's also inside this gearbox that we can't see, there's actually another fixed reduction. So for and it's what Bill talked about, the sprocket is a fixed ratio. So for example, to calculate the gear ratios in the transmission, we have a fixed ratio of 2.19, and these are the 6 gearbox ratios that we have.
I see. Okay.
So yeah, so that's a good question.
Thank you.
So going to Baja's, so let's just look at so if you look at Baja's car is a little bit weird in that it gets limited at 3,800. So you see they basically, for all these gearbox ratios, you come into idle until about 5 miles per hour, and then you go into and this is just your pulley grabbing on the CVT. So they run a belt and pulley CVT. I was hoping it would show more than a belt. So they run something like this. So initially it's not even engaged until this one comes and grabs it. So that's how it kind of has a clutch in it. And so what's basically happening is it's going to grab in, and then you're going to be in that very first gear for a while until it starts to shift. And then hopefully it shifts at this peak power RPM, which for us is pretty high, like 3,800. And you can see again, like here's the final velocity versus the gearbox ratio. So there's something up with the way it's running right now. Let me see. I don't think it might not be running to enough time. No, that should be fine. 30 seconds. No, this is formula. Baja. Let's run it for a while, 30 seconds. And let's run like gearbox ratio of like 1, 5, and 10. Just try the bounds basically. Ooh, that was a little unhappy. Let's do 2, 5, and 10. I might go a little crazy with that. So while it's running, so you can see we calculate the torque basically, calculate the drag, the rolling resistance, and we get and this is the force on the tire from the torque of the engine. So we get all of those. So you see basically gearbox ratio 2, you can't put a lot of tractive force in the ground basically. But once you get up to gearbox ratio of 10, you kind of begin to spin the tires up here. So here you can see 2 never even starts to shift. And so you can see the final velocities basically. So 5 and 10 are both reaching kind of this final miles per hour of like 26, 27. The gearbox ratio of 2, you see like almost never reaches it. I don't know why the top speed is so low. It's probably the rolling resistance is pretty high or something. But here you can get to see like the time to reach 100 feet. It gets lowest, around 5, and then it's going to come back up when it gets to 10. And so you can, I guess with that, I wanted to kind of show kind of the behavior of the vehicle basically. Let's see here. This is pretty high. Let's make this like 0.05. That's probably more realistic. And let's dial it in a little bit. So let's do something closer, like 4, 5, 6. Oh, let me see here. Let me make sure too I didn't make this 4-wheel drive. There's a little part here where it sees if the tire is slipping. Yeah, so this is for 4-wheel drive. They're kind of playing with some numbers. Wait. Oh, the weight distribution's in there. Let me see maybe I set the weight distribution to 1. No, it's still 0.6. Okay, no, that should be normal. All right, so here's the gear ratio of the CVT versus the velocity. Here you can see the different tractive forces. So I wanted to look at. Okay, so here we're getting a little better. We're all kind of converging. 0 to 35. So all, let's see here, 1 to 2. I guess they're all pretty close to each other. So you can see you can go a little bit faster with the gearbox ratio of 6, right? To reach like 100 feet. So yeah, so let's play around with the Formula One a little bit more. So we use around a 4, gearbox ratio of 4. So let's look at what happens if, you know, so we can look at, let's look at our, we can look at kind of the behavior. So you can see we kind of come, we shift around the peak one, and then we come up here till we hit the max. And here we're getting limited at about 60 miles per hour, it looks like. Since these are not scatter plots, they're not giving us the actual values. Can make this a scatter plot. Hopefully it doesn't not like me because of that. Oh, that's not even the right one. We wanted to do this first one. So if we look at this, what's our favorite one? Here it is. So you can see it takes us to reach 246, the sprocket ratio 4, just over 4.5 seconds. So let's see what happens. And you can kind of see the shifting of it here. So let's see what happens. Let's see what happens if we only used like gears. If we only tried to use gears 3, 4, and 5 or something. So we said, hey, I'm gonna copy this so I don't lose it.
Chris, are those the actual ratios of those gears
Yep.
in our transmission?
Yeah. So well, that's what the manufacturer gave us at least.
I know that a lot of schools disable some of the ratios.
Yeah, I don't think we might not need some of the higher ones, to be honest with you, like this. And we probably don't need 6, to be honest. I don't know if we could actually on our course shift through 6. But depending on which ones you pick, you might pick a different gear ratio, because these gears are going to be at these gears. You'll notice they're closer together. The first 3 are further apart. So you might disable your first 2 and just run with these 4 gears that are kind of closer together, because we're going over a narrower speed range than a typical car, right? We're going like 0 to 40 or 50 miles an hour, you know? We're not going 0 to 150. So you might pick these so you can help you kind of shift more frequently.
What you might want to do is use the lower one to get you up to some speed, skip a couple, and then just rely on high gear.
Yeah, I mean, the only thing is, right, like we can pick the sprocket ratio. So we could make 1.3. So instead of, you could either use this and a low sprocket ratio, or we could use these and a high sprocket ratio, right? So we can, because we can change the fixed gear ratio. So we could take like all 4 of these and we could center them to be good around like 5, 10, 15, 20 miles an hour. Or we could make this like 5, 15, 25, 35, 40, 45, right? So because we can change the sprocket ratio, which I'm kind of messing around with here, you can actually, it's more about the relative of those gears ratios, because you can really, you can change this basically. So, but you'll see here, like, so if we knock out the early ones, it's going to shift way late, right? And you'll see that should really slow us down. Gear 1.
Is high gear transmission an overdrive?
Like, yeah, one of those, exactly. So like, this I mean, it's never really overdrive because it's 0.87 times 2 times this gear ratio. So the gear ratio is all multiply. But yeah, so these, most people would call like these overdrive. Inside the box, they're higher than 1-to-1.
I was told if you buy a car with like a 7-speed transmission,
Yeah.
you're getting a 4-speed transmission with 3 stages of overdrive.
Huh.
Five,
I mean, yeah, that's interesting. But for me, it's like whether this ratio goes over 1-to-1 is a little bit arbitrary because I could make this 1-to-1 and make this 4, this gear ratio, like the fixed gear ratio 4, and the whole thing together would be 4. Or I can make this overdrive at 0.5, and I can make this gear ratio 8, and I would still be at 4, right? So it's like since the gear ratio of your transmission gets multiplied by the final drive, it really depends on the multiplication of all of them. If that makes sense.
I would think that the best thing to do is to have a low gear to get it off the line. And once it's a certain speed,
Yeah.
go up a couple ranges and then find a range run between, say, 25 and 40 or 25 and 50, without really shifting. Does that sound reasonable to you?
Yeah.
I think shifting is going to be
An issue.
a distraction.
Yeah, I think you might be right. I think you might have like more gearing to accelerate, but then you don't have a bunch of gearing in the turns. Yeah, I mean, it could be interesting. What I would do to start is to have all of them, just use all of them and see how it goes, basically.
Right.
And then if we find we don't use them, then we don't use them, right? But I think we have all 6 in there working. We might as well center it around those 6 and then figure out, see what happens.
I think that the guys will eventually decide on their own where they want to drive the car, what gears.
Yeah, exactly. But so for example, so for example, you saw that was shifting super late. But if I change my sprocket ratio to 8, you'll see it's all of a sudden not going to look like it was shifting so late. So now it's shifting at like 15 miles per hour. So now we're shifting actually kind of early. We're still not going to do as well on time, right? We're still going to do bad on time because we don't have that many gears. But I think ideally, if you want to get the best time, so we could try a couple of different ones of these, a couple of different sprocket ratios, 2, 4, 6, 8. And if you could, in terms of just, well, we're just talking pure time. I mean, Bill's right in that it's going to be hard to shift in these corners. You know, if you could, if the car could shift on its own and you had 5, 4, 3, and you had all these gears, and you had, 0.5 or something, and this would really, I mean, you see, you're going to be shifting a ton, and this would be like 1, 2, 3, 4, 5. So you can see for like one in this purple, kind of hard to see. I'm trying to pick out one color you can actually see. I guess the blue you can see. You shift once, shift twice, shift 3 times, shift 4 times, shift 5 times, shift 6 times, 7 times. But you can see this line right here. This is your propulsion limited line. That's what we were showing in this curve over here, right? We're saying, hey, if you could do as best you can, perfect, you'd sit right on this propulsion limited line. So you can see if you have a lot of gears, it really lets you sit on this propulsion limited line. You're sitting right there, max power, which is good. And then you can see, let's see here. You can really get your times down though. So you can see here, you get we got a 4.6. That's one of the lowest ones we've seen so far. And even 2 gets you pretty fast, I guess, down to if you add those high gears for you. So, but anyway, so that was more just to show you the, show you that we have this tool, and just to try and understand kind of the physics of the car as it's accelerating, basically. So Baja, it looks like this: drive belt slipping, it's speeding up in low gear, and then it shifts all at this peak power, basically. So the Baja engine, interesting enough. So if you could make a better CVT, what that would really involve would be if you could make it shift across a huge range, right? So it only can go from a factor of about 4. You could maybe have it shift from a gear ratio of 10 to 0.5. Then, I mean, that would be really hard to do mechanically. I mean, that's just a hard thing to engineer, something that shifts. It goes from, you know, it changes that drastically. But here you basically stay perfectly on the, you know, quickly you get up to your max power and you sit at your max power the whole time. Because you can start off in that really low gear. So where was the one with the gear ratios? So basically you start off at 10 and you start shifting basically right away. And then you get, let's see here, this is interesting. So you can get low times. We'd even have to go lower, it looks like. Let's see how low it would go if you had a really good gearbox, really good. So maybe you could go like 1, 2, 3. So this would be our gearbox ratios because we build a gearbox for this.
And the time, like in the manual that you had, when you shift, that delay is just the delay of it engaging.
For the CVT or for formula?
For formula.
For formula.
Like every time it dips from that curve, is that just from like the fact that you have to put it in a new gear?
Oh, when it shifts off the optimum curve?
Yeah.
Oh, so that's really because, so here's like, here, pretend you're on this purple line. It's because you're going off of max power. So you basically, because you're in a fixed gear, you have to go off of max power and then you drop below and you drop below max power and then you get back into max power. So it's not actually a time thing. It's because since you're shifting around max power, instead of just ideally sitting right at the perfect max power, like Baja can do with the CVT. Keep in mind though, a CVT is not a very efficient system. So the power you lose by being slightly off max power is probably better than actually the losses in having a friction belt. But it's, yeah, so going off that peak is really about getting away from your max power basically, because you're no longer getting the power that you'd expect. Anyway, so I'm about to hop into another group meeting, but yeah, so today, right, so we talked a lot about engines, right, and about basically getting in as much air and fuel into here as possible, getting some of the timing right, getting the right mixture of air and fuel, right? I mean, that was kind of a lot of it what it was about. And then we talked about how can you design your car so that you sit near max power as long as possible, right? And so we did a little bit of the kinematics, right, of the gears. And really, you know, ideally you want to stay right here, but of course, formula shifting up and down and around that point. And yeah, so I guess with that, you know, you guys can, I'll post up some of these tools and so you can kind of start to play with them. If you have any questions about them, just let me know. But you can, if you have MATLAB, you can basically start to try different where's Baja's? This is Baja's. So Baja can try like different CVT ranges and then try different gearboxes. You could also see like what would be more important, to double grip of your tires or to double your engine power. You know, you could, this is, you know, there's no limits to what you can kind of analyze. Not that it's all useful, but, or you could try like, hey, if we had to pick 4 of these, what would we pick? And if we pick those 4, the optimal gear ratio of our sprocket will move around. So for example, if you pick these 4 high numbers, your sprocket should be a little lower than if you pick these 4 numbers, then your sprocket's got to be a little higher to make up for it, right?